Last video, we discussed the concept of a matrix transformation and we defined it. In this section, we want to look at how much information do we actually need to know about a matrix transformation in order to find a matrix A. In the last video, we were mostly talking about matrix transformations where A was given to us. Here, we're going to be given some information about this transformation and see if we can figure out what A should be. So for example, suppose we have a matrix transformation T that goes from R2 to R2, and we only know that T of 1, 0 equals 3, 2, and T of 0, 1 equals negative 1, 4. So we know where this transformation takes these two specific vectors. Is this enough information to find A? So let's consider this particular example. We want to know kind of in general, what is, T of x1, x2, right? This would be sort of our general question. And so, one thing we can recognize here, and this is going to be A times x1, x2. So one thing we might recognize here is the fact that our vector x1, x2 can be written as x1 times 1, 0 plus x2 times 0, 1. And so if we're looking for A times x1, x2, that's the same thing as looking at A times x1 times 1, 0 plus x2 times 0, 1. But if we go back and look at some of our properties of matrix vector multiplication, we may recall that we can distribute a matrix, into a vector sum like this, and also rearrange how the scalar multiplication works. So, again, using those properties of matrix vector multiplication, this can be rewritten as as x1 times A times 1, 0 plus x2 times A times 0, 1. But we know what A times A times 1, 0 and A times 0, 1 are, because that's essentially what our given information is, right? So these two pieces of information are given to us up here. This A times 1, 0 is T of 1, 0, and this A times 0, 1 is T of 0, 1. So in this formula down here, we can replace each of those. So this becomes x1 times 3, 2 plus x2 times negative 1, 4. But this is exactly the same thing as taking the matrix, whose columns are 3, 2, and negative 1, 4, and multiplying it by the vector x1, x2. And so what we've discovered is that, this matrix A times x1, x2, which is what we were essentially looking for to begin with. We were trying to find this matrix A, is exactly given by the, it has exactly the columns whose vectors were given to us in those original pieces of information. And so it turns out that if we know T of 1, 0 and T of 0, 1, that is enough information to find A. And in particular, A is just going to be the matrix whose columns are exactly equal to the outputs of each of those vectors. Generalizing this a little bit, first of all, these vectors, 1, 0, and 0, 1, we often will denote by E1 and E2. And we will sometimes call these the standard basis vectors of R2. This idea of a basis is an important one in our class, but not one that we'll talk about for a little bit. So, keep that idea in mind. But for now, we'll just know that when we say, vector E1 in R2, that's going to be the vector 1, 0, and vector 0, 1 in R2, that's going to be this E2 vector. More generally, we can talk about the standard basis vectors in Rn. And so we'll have n of them, E1 through En. These are going to be the vectors. So, sort of the general Ej vector will be the vector that has zeros everywhere, except for the sort of jth spot, it's going to have a 1. This is the jth spot. So E1 has a 1 in the first spot. E2 has a 1 in the second spot. E3 would have a 1 in the third spot. En has a 1 in the nth spot, right? So, the idea here is we've got n of these. They're mostly zeros with a 1 in just one spot. So going back to that first example, we can generalize this. This is proposition 256. If T is a matrix transformation going from Rn to Rm, such that T of x equals Ax, then the matrix A has columns T of E1, T of E2 through T of En. That is, A is going to be given by the matrix whose columns are the vectors T of E1, T of E2 through T of En. So as long as we know what the what this matrix transformation does to these standard basis vectors, then we can construct this matrix. So let's look at a few examples. Suppose we've got this example here where T goes from R2 to R2, and we know T of E1 is 2, 5, T of E2 is negative 1, 4. Then the matrix, this is sometimes called the standard matrix, but the matrix for this transformation is just going to be the matrix whose columns are 2, 5, negative 1, 4. Next one here, suppose T goes from R4 to R4 such that T of x equals negative 2x for all x in R4. So we want to find the matrix for this transformation. We just need to know where T takes those standard basis vectors. So T of, for example, E1, which is 1, 0, 0, 0 in this case, is going to be negative 2 times 1, 0, 0, 0, which is just going to be negative 2, 0, 0, 0. And the same kind of thing will happen for E2, E3, and E4. So I'm not going to show all of those. Hopefully you can kind of see how we can generalize this. The matrix for this transformation will look like this. It's going to have zeros everywhere except for down that main diagonal where it's going to have negative 2's. Next one, suppose T goes from R2 to R2, where it is going to reflect every vector over the x1 axis. So sort of a geometric description here. In this case, we're thinking of that horizontal axis as the x1 axis. And so we're, reflecting over that x1 axis. So if we were to think about where E1 goes, so E1 is going to be, geometrically in R2 is going to look like that, and E2 geometrically looks like that. Right? E1 is 1, 0, E2 is 0, 1. So if we think about reflecting each of those over the x1 axis, well, E1 is on the x1 axis, so it's not going to change at all when we reflect it. So T of E1 is just going to equal E1. So that's just 1, 0 again. If we reflect E2, that's going to end up being the vector 0, negative 1. We reflect it over the x1 axis, I should say. So our matrix A in this case is going to be the matrix 1, 0 in the first column, 0, negative 1 in the second column. And you can test, we give a little example here, right? That T takes 3, negative 4 to 3, 4. You could test that. If we multiply A by 3, negative 4, you would see that the output would be, in fact, 3, 4. And this would have that effect on any vector. We're going to talk about the geometry of these matrix transformations in the next section a bit more, but doing a few examples here, every vector under this transformation will get reflected over the x1 axis. One more example here, talking about a rotation. Suppose T goes from R2 to R2 and it rotates every vector counterclockwise around the origin by an angle theta. And so just to draw a picture here, P of E1 would be rotated from the 1, 0 position by an angle theta in the counterclockwise direction. Look like that. And then T of E2 would end up over there. And so we sort of need to figure out what the coordinates of these endpoints of each of these vectors would be. If you think back to some trigonometry, you might recall kind of what's going on here. The point 1 comma 0 as a sort of starting point is a point on the unit circle. And as we rotate these vectors around by an angle theta, we are going to still end up with, points sort of on our unit circle. We continue this all the way around, the little dotted line unit circle there. And so rotating the point 1, 0 by an angle of theta gets us precisely to a point whose x coordinate is given by the cosine of theta and whose y coordinate is given by the sine of theta. So the vector t of e1 will just be precisely cosine theta, sine theta. T of e2 similarly will be related to cosine and sine, except it's not just cosine and sine of theta, it's going to be cosine and sine of theta plus an additional 90 degrees. So we could write this as cosine of theta plus 90 degrees, or if we were working in radians, we could put pi over 2 radians, and this one would be the sine of theta plus 90 degrees. We may recall from some trigonometry that the cosine of theta plus 90, one of our identities that we hopefully saw at some point in our math career, is equal to negative sine theta. And the sine of theta plus 90 degrees is precisely equal to the cosine of theta. And so T of E1 is cosine theta sine theta. T of E2 is negative sine theta cosine theta. And so our matrix A, if we're talking about rotating by an angle theta, is going to be given by a matrix whose first column is cosine theta sine theta, and whose second column is negative sine theta cosine theta. So if we wanted to be more specific, we could say, what matrix would we get when we rotate by 30 degrees or 45 degrees, or maybe working in radians by pi radians, right? And we could plug in a particular example there. And here's this sort of general form for that, which is nice. We'll be looking more at the geometry of these matrix rotations in the next section and in the next video.